Good day, guys. Today we're taking deep learning off the data center rack and putting it on a device that fits in your hand. By the end of this session, you'll have trained an image classifier, shrunk it down, and run it live on a Raspberry Pi, and you'll have the numbers to prove the optimization worked. So this is a build session. We'll move through the whole pipeline together, and you'll do every step yourself in the lab. Not long ago, running a neural network meant a powerful GPU and a lot of electricity. That's changed on two fronts. The models got leaner and the small boards got stronger. That combination is what makes edge AI real. And it buys us four things. Latency. The inference happens right on the device, so there's no trip to the cloud and back. Privacy. The image data never leaves the board, which matters a lot for cameras. Offline capability. It keeps working with no network. And efficiency. It runs inside a tight power and memory budget. That's exactly what robotics, IoT, security, and real-time monitoring need. Here's what you'll walk out able to do. First, configure the environment. Get the vision and deep learning packages working. Second, integrate a camera on the Pi. Third, train the classifier. Fourth, deploy it on the board. And fifth, the part people skip, actually compare the baseline against the optimized version. Keep that fifth one in mind the whole time. Optimization only counts if you measure it. This is the map for the whole activity. 6 stages: configure, capture, train, convert, optimize, benchmark. Here's the key idea. Notice the split. Training and conversion happen on your workstation where you have the horsepower. Only the finished, optimized artifact ships to the Pi. So the Pi never does the heavy lifting of training. It just runs the lean model we hand it. Keep that mental model as we go. Let's start at the bottom. Everything sits on the OS and drivers, Raspberry Pi OS, libcamera, the camera stack. Above that, your vision libraries, OpenCV, Pillow, NumPy. Then the deep learning framework you train with. Then the inference runtime, TensorFlow Lite or Lite-RT. And finally, your application on top. The checklist on the right is the order you'll actually do it. Flash and update the OS, make an isolated environment, install the libraries, install the runtime, check the drivers and camera. One tip that saves hours: pin your package versions. If the host and the Pi run different versions, the model can behave differently, and that's a miserable bug to chase. For steps to get the camera, feeding the model. Connect it, ribbon cable to the CSI port or a USB webcam. Enable it in raspiconfig. Capture frames with Picamera 2 or OpenCV. And then pre-process. That last step is where a lot of projects quietly break, so look at the panel on the right. The rule is simple. The frame you feed the model has to match what the model saw in training. Same resolution, usually 224 by 224. Watch the color order because OpenCV gives you BGR, while the model probably wants RGB. Normalize the pixels the same way you did in training. And match the data type, UINT8 for a quantized model, Float32 for the baseline. Get those 4 right, and your accuracy holds up. Get 1 wrong, and the model looks broken when it isn't. Now we train. Collect and label your images, split them into train, validation, and test. Pick an architecture. Train it, watching validation accuracy. Evaluate honestly on the test set, confusion matrix, precision recall. Then export the baseline. 2 pieces of advice. First, prefer transfer learning. Start from a pre-trained backbone like MobileNet or EfficientNet Lite and fine-tune. You'll need fewer images, you'll converge faster, and you'll get better accuracy on an edge-sized model. Second, design for the target from a start. A model that trains beautifully on a GPU can be far too heavy for the Pi. Pick your input size and depth with the board's memory and latency budget already in mind. Here's a point most students miss. A trained model is not a deployable model. You have to convert it. The flow is straightforward. Take the trained network, run it through the converter, and you get an edge artifact, a TF Lite or Lite-RT flat buffer. On the device, an interpreter loads that file and runs it. Why bother? 3 reasons. It's smaller because the format strips out ops you only needed during training. It's faster because the runtime is tuned for ARM CPUs and accelerators. And it's portable. 1 artifact runs across many edge devices. So conversion isn't a formality. It's what makes deployment possible. Now the fun part, making the model leaner. For techniques worth knowing. Quantization stores the weights in 8-bit integers instead of 32-bit floats. That's up to 4 times smaller, faster on integer hardware, with minimal accuracy loss. This is the one you'll use most, and we'll dig into it next. Pruning removes the weights that barely contribute, leaving a sparser network. Knowledge distillation trains a small student model to imitate a big teacher, transferring the accuracy into a compact form. And operator fusion merges adjacent operations, convolution, batch norm, and activation, so the runtime executes fewer, faster kernels. You can stack these. But if you only learn one today, learn quantization. So what actually happens in quantization? Full precision spends 32 bits describing each weight. Quantization maps that range onto 8-bit integers using a scale and a 0 point. That's the little formula on screen. Real value equals scale times the quantized value minus the 0 point. You've got 3 flavors. Post-training quantization is the easy one. Take a train model and quantize it, no retraining. Quantization-aware training simulates the int8 behavior during training, so you recover the most accuracy. And dynamic range sits in between. Now look at the chart. Compared to the baseline, the quantized model is roughly a quarter of the size, meaningfully faster, and it holds almost all of its accuracy. That's the whole pitch. You give up very little and gain a lot. This is the objective that separates a demo from engineering. You deploy both models, baseline and optimized, and you measure the same things under the same conditions. 5 metrics: latency per inference, model size on disk, accuracy on the test set, throughput in frames per second, and peak memory. The table shows the pattern you should expect. The optimized model is around 4 times smaller, it responds faster, it pushes more frames per second, and its accuracy drops only slightly. But, and this matters, report your own numbers. Hardware batch size, even how hot the pie is running, will shift these figures. The point of the lab is the measurement, not my example values. Optimization isn't one size fits all. It's a negotiation between size, speed, and accuracy, and the right choice depends on what's actually constraining you. Need lower latency? Quantize to int8, enable operator fusion, maybe add a hardware accelerator. Tight on memory? Quantize and prune, and start from a smaller backbone. Is accuracy non-negotiable? Use quantization-aware training, or keep your most sensitive layers in float. Running on intermittent power? Go for the lightest model and duty cycle the inference. So before you optimize, ask, which of these is hurting me most? Optimize for that. All right, this is where you take over. 6 tasks, and they mirror everything we just covered. Set up the environment and verify it. Integrate the camera and pre-process a live frame. Train or fine-tune a classifier on your dataset. Convert it and run it on the Pi. Apply quantization and redeploy. And finally, benchmark both versions and write up the comparison. That last task is your main deliverable, the numbers and your interpretation of them. Work through it in order. Each task sets up the next. For things to carry out of this room, Edge AI is practical, and SBC can run real deep learning when the model is prepared for the target. Conversion is mandatory. Training and deployment are separate steps, and the edge needs a runtime-ready artifact. Optimization pays off, quantization shrinks and speeds up your model for a modest accuracy cost. And always measure, compare baseline and optimized on the same device with the same metrics. Do that, and you're not just running a model on a Pi, you're doing Edge AI engineering. Now, let's get into the lab.